Welcome back to Java Internal's Crashcasts. I'm your host Sheila, and today we're diving deeper into the world of atomic variables. We're currently in the second season, Synchronization Utilities, and this is the third chapter focusing on atomic variables. In our previous episode, we covered atomic integer, atomic long, atomic boolean, and atomic reference. Today, we're exploring atomic integer array and atomic long array. Victor, are you ready to unravel these atomic arrays for our listeners?
Absolutely, Sheila. I'm excited to discuss these powerful tools for concurrent programming. Before we dive in, listeners should be familiar with basic Java concurrency concepts and have a good understanding of regular arrays in Java.
Great point, Victor. Now, let's start with a quick quiz for our listeners. Here's the question. In a multi-threaded environment, what potential issues might arise when multiple threads try to update elements in a regular integer array simultaneously, and how might atomic integer array help address these issues?
That's an excellent question, Sheila. It really gets to the heart of why we need atomic arrays. Listeners, take a moment to think about race conditions, visibility problems, and the concept of atomicity. We'll reveal the answer at the end of the episode, but for now let's break down the key components of atomic integer array and atomic long array.
To start, can you explain what exactly atomic integer array and atomic long array are and how they differ from regular arrays?
Certainly. Atomic integer array and atomic long array are classes provided by Java's concurrent package. They're essentially thread-safe versions of integer and long arrays. Unlike regular arrays, these atomic arrays ensure that operations on their elements are atomic, meaning they happen as a single, indivisible unit, even in multi-threaded environments.
That sounds useful. Can you give us an analogy to help visualize how these atomic arrays work?
Sure. Think of a regular array as a row of safety deposit boxes in a bank, where multiple people, threads, have keys to access and modify the contents. An atomic array, on the other hand, is like a high-security vault, where each box has its own security guard. When someone wants to access or modify a box's contents, the guard ensures that only one person can do so at a time, and that the operation is completed fully before anyone else can access it.
That's a great analogy. Now, how do we create and use these atomic arrays in our code?
Creating an atomic integer array or atomic long array is straightforward. You can initialize them with a specific length or pass an existing array to the constructor. For example, you could create an array of 10 elements or initialize it with specific values. To access or modify elements, you use methods like get, set, getAndSet, compareAndSet, and various atomic update operations.
Interesting. Can you elaborate on some of these atomic operations?
Of course. Let's take the getAndIncrement method as an example. This method atomically increments the value at a given index and returns the old value. It's equivalent to I++, but it's thread-safe. Similarly, there's getAndAdd, which adds a value to the element at a specific index atomically. These operations ensure that no data races occur, even when multiple threads are accessing the same array elements concurrently.
That's fascinating. It seems like these classes solve a lot of concurrency issues. But I'm curious, are there any performance implications when using atomic integer array or atomic long array compared to regular arrays?
That's a great question, Sheila. While atomic arrays provide thread safety, there is a slight performance overhead compared to regular arrays. The atomic operations use what's called compare and swap instructions under the hood, which can be more expensive than simple reads or writes. Compare and swap, or chaos, is a low-level technique that helps ensure atomicity. However, in scenarios where you need thread safety, the performance of atomic arrays is generally better than using explicit synchronization on regular arrays.
I see. So it's a trade-off between safety and raw performance. Can you give us an example of a real-world scenario where atomic integer array or atomic long array might be particularly useful?
Absolutely. One common use case is in concurrent counters or statistics tracking. Imagine a web server that needs to keep track of the number of requests for different endpoints. You could use an atomic integer array where each index represents a different endpoint, and multiple threads, handling different requests, can safely increment the counters without explicit synchronization.
That's a great example. Now, how do these atomic arrays compare to other concurrent collections in Java?
While atomic arrays are great for specific use cases, they're not always the best choice. For example, if you need a dynamically sized collection, you might consider concurrent hashmap or copy-on-write array list. Atomic arrays have a fixed size and are best suited when you know the size in advance and need fine-grained control over individual elements.
Got it. Are there any common pitfalls or misconceptions about atomic integer array and AtomicLongArray that our listeners should be aware of?
One common misconception is thinking that because the array is atomic, all operations on it are automatically thread-safe. While individual operations are atomic, sequences of operations may not be. For example, checking if an index is within bounds and then performing an operation is not atomic unless you use a method that does both, like get and increment.
That's an important point to remember. Do you have any best practices or tips for using these atomic arrays effectively?
Certainly. First, use the appropriate methods for compound operations. For instance, use get and add instead of separately getting a value, adding to it and setting it back. Second, be mindful of the array size. Since it's fixed, ensure you allocate enough space initially. Lastly, consider using the weak compare and set method for better performance in scenarios where you can tolerate occasional spurious failures.
Those are excellent tips, Victor. Now, before we wrap up, let's reveal the answer to our quiz question. Can you explain why atomic integer array helps address the issues with regular arrays in multi-threaded environments?
Certainly. In a multi-threaded environment, regular arrays can suffer from race conditions where multiple threads might read and write to the same element simultaneously, leading to lost updates or inconsistent states. Additionally, there can be visibility issues where changes made by one thread aren't immediately visible to others. Atomic integer array solves these problems by ensuring that all operations on array elements are atomic and that changes are always visible to other threads, thanks to the happens-before relationships established by the atomic operations.
Thank you, Victor, for that comprehensive explanation. To summarize today's episode, we've learned about atomic integer array and AtomicLongArray, their thread-safe operations, performance considerations, and real-world use cases. We've also discussed best practices and common pitfalls to avoid. In our next episode, we'll be wrapping up the atomic variables chapter with a summary of what we've covered. Don't miss it. If you've enjoyed this episode, please subscribe to Java Internals Crashcasts and leave us a rating. Your support helps us continue bringing you in-depth explorations of Java's internals. Until next time, happy coding.